Hi, I'm Brian Wandell, and I'm here to have a conversation with Dave Brainerd
And I'm
and
Dave Brainerd at the University of Pennsylvania.
Joyce Farrell.
Hi, Joyce Farrell here.
And the three of us have all put a lot of effort and various ways into the software system that we're going to talk about today, which is the image systems engineering toolboxes of various sorts. David's preparing a lot of different detailed tutorials, various tutorials about specific parts, and I'll be preparing a few. Joyce will be contributing to these to this conversation also. But to begin with, we want to just give you an overview of the collection of repositories that exist, so that if you're looking to do a particular thing, how we use them, and if you're looking to do a particular thing, how you might find stuff. And maybe send us a message if you don't see it, and maybe we have it somewhere. There's a big collection of stuff, and we'd like to share it with you, and we hope it's useful for you. So, David, you've been using this for publishing papers, right?
Among other things, yeah. And I think my focus has been, mostly on trying to model the initial coding by the human visual system, which is one thing that pieces of this software are focused on. I know you use it as well for camera simulation, which is an interest of mine, but not something I mostly do by watching you do it.
Yeah,
and
we'll say a little bit about that. And Joyce, you've been doing it for medical imaging applications?
Yeah, maybe I'll describe that. Recently, we've been using it for designing new types of imaging sensors for medical applications. But as you say, you'll go over the work that we did early on for the camera phones.
Yeah,
There's a picture there.
Yeah, there is. And this is kind of the early days. David has built a lot on top of this. We've continued to build on top of it too. But there's a kind of a core to the image systems engineering toolbox, which we've recently labeled ISET. You'll hear ISET a lot for image systems engineering tools. And this one's for cameras. And this is some code that kind of sits at the bottom. It's all the other repositories rely on the kind of fundamental things that are in here. And there are some principles for this toolbox. We really tried hard. We're always stressing out about making sure that we're getting things in quantitative units with quantitative radiometric properties of the scene. You'll see that in some of the demonstrations. And for today, we'll pretty much be talking about scenes and illuminance, getting the inputs to the system right. It's a lot on that. And in future recordings, we'll say more about the optics, and we'll do that soon. And first, it includes models of simple optical elements, just like diffraction limited elements, or simple lenses like double Gauss lenses, or even micro lens arrays and so forth. But for the human eye, it's particularly strong, and that's a place where we have models of the human eye and measurements of the human eye. And David and Nicholas Kataris and others have really embedded that in a solid way for those of you who are interested in human eyes. So let me say that—
by the way, Brian, before you go too much further, maybe you ought to just say where it is that this page that you're going through is.
Good. So this particular page, you can see the link up top here, github.com ISET, sits over here. And there are a lot of repositories here. Let me just, I'm just scrolling through for doing all kinds of things. And I'll touch on a few of them as we go through today. But each one of these builds on the repository that we were just looking at. Okay, so this is inside of the base of ISET. There's a parallel one, which I should point to, that David and Nicholas and others have really focused on, which is called ISET Bio. The biology part became so big and so significant and has so many special features that it too has a whole bunch of repositories. And I'll mention some of them. I know, David, you use this one a lot for psychophysical modeling.
Yeah, that's a repository with code that wraps on top of the ISETCam, ISET Bio system, and it's focused on making it easy to simulate ideal observer, computational observer thresholds, and we'll have a video about that one at some point.
Yeah, and many of these will have their own, special things. I know David's been talking to me about eye movements and modeling eye movements, and that's a work in progress. David and I wrote some review papers, and also recently we published a journal paper that also depends on these toolboxes and includes various figures and shows how we derive the figures in the paper using these tools. So, but then back to the basics, back to the what we had in mind when we did this, when we did the ISETCam implementation. So we try to keep things neat, everything inside of folders and with folders that are kind of meaningful. And we do our best to help you with notes. We usually, when you go to one of our repositories, there will be a wiki page, sometimes even something more elaborate, one of those github.io pages. And usually those pages will describe what it is the purpose of that repository. And this particular page was the one that was kind of the foundation from way back in the day. And over here on the right, you can navigate your way through different kinds of instructions about how to install it and how to use GitHub if you're not, all that familiar with it. And we always try to say some things about how it is we organize the code itself. And we'll give you lots of some examples coming up. But in all of these repositories, there's usually some important concept that really matters. Today, it's all going to be about the scene, but there are several concepts throughout. There's the scene, the optical image, it might be the retina or cones more specifically, and then the retinal ganglion cells, or it might be, in Joyce's case, a sensor or a particular type of sensor or a particular type of light source. And whenever there's something important, we promote it to be an entity, like an object, or those of you familiar with programming, these are objects or classes, or they're implemented as special things. And the scene is obviously very special. And whenever you have something like that, you can create it, you can set its properties, you can get its properties. There are various compute things you might do with it, ways to plot it, and there's usually a window where you can visualize what the parameters are in those properties. And we'll spend a fair amount of time today. I'll illustrate scene create. And there's also a, we try to be good about naming things. So if something's created that's intended to deal with scenes, we'll do something like we'll usually prepend scene to it because the scene's an important object. And in Matlab, if I do scene tab, you can see, oh gosh, there's a whole lot of functions here that all have to do with creating scenes, interpolating scenes, setting properties, showing them. There's just a lot of things that have to do with scenes. And you can find things more easily by the namespace. If it was something like a sensor instead of a scene, you could see all the different functions. Sensors are very important for things that we do. So we try to keep the namespace clear. And for general functions that are all related to image systems engineering, we usually keep IE as the thing. These are all the different utility functions that aren't particularly attached to any particular object. So things really start with IE. Is the way we've been preserving the namespace. Okay, so I think maybe what did I forget? David, Joyce, what do you think I should have, if you were starting, imagine one of yours. We're trying to do this in a way that if we had a student.
So I think that's great. I think that as you say, the scene is really the point of departure for doing most anything, because in our modeling of cameras or our modeling of the image vision system, there's usually a stimulus, and the scene is how we specify it in most cases. And I think you'll probably talk about perhaps some other ways one can do that with 3D scenes, but often they're on displays. And last week we recorded a video where we talked about a pipeline that began with the scene. And so here we are thinking about that. But I think the goal today is to sort of unpack that first step and show how you can manipulate it and set it up and probe it. And that's going to be key to doing very much with this set of software. So it's a great place to dive in.
Yeah, I just want to append to that when we started this, it was focusing on camera phone for ISETCam at least. And so the scenes had to be representative of actual scenes in the world. So displays are part of that, but we really had to think about how a camera was going to be capturing an image.
You know, that's right, and we'll get to that, and that's important. I was going to say that, Joyce, you reminded me how in the early days, because of the camera phone thing, we created lots and lots of test scenes like sweep frequencies and slanted edges and these rings and rays and things of this sort. So there are test scenes. They're the ones that the psychophysicists use, like these spatial frequency charts and so forth. And then there will be much more complex scenes, scenes that involve objects and faces and so forth.
Right.
And yeah. So and David's important case of scenes that come off of displays is for some people that's really the most important one.
Yeah, that was important for us when we looked at them, and people were going to look at them. So actually that was really important for us too, because part of it was image quality, and in the end somebody was going to look at an image. Yeah. So going from the scene that was captured by the camera and going into the display, there were a lot of utilities built for that.
Yeah. And maybe it's worth commenting, when we do psychophysics, there's a display often and the stimulus is on the display, and we now have started specifying our psychophysical stimuli as ISETCam scenes, and from there moving them through our experimental software so that in the end we have both the stimulus recorded, what was in the experiment, have it available for modeling, but literally we move the description of the experimental stimuli through this data structure that we're going to talk about now.
And you're reminding me, David, that's right. We have all this, things about displays and display models in here. But you're reminding me that, before David worked with us on these ISET tools, he developed this wonderful package that's so widely used in psychophysics, the Psych Toolbox. And he did that with Dennis Pelly, as I recall. Dennis and you were kind of partners in this.
That's right.
And we've made an effort here to be able to move back and forth when needed. So display modeling and characterization from the Psych Toolbox and the modeling for digital twinning that we use here. We're doing our best to kind of keep things consistent and keep the units consistent and keep our code consistent. Okay, so I was going to say that in the wiki, we often do this. You can see these are tutorials and scripts. I'm going to run through a particular script today, but we have various tutorials and scripts, and you can find them from the wiki. So if you want to know about tutorials and scripts from the scene, you click on scene, and there are various things that we think will be useful to you here, but included in that is links to the code. Literally, I'm going to go through this script or something very close to the script today, and you can find that you can find all those links for how to do these things and how to do different kinds of calculations. That's both software these are functions inside of the repository, and they're also linked to here. That we made them available as HTML files so that you can just read them online and get a sense for how to look things up. And we're kind of hoping that the large language models are crawling these websites and incorporating them into their knowledge base, so that you can just ask ChatGPT to write a little bit of ISET code and it'll do it for you someday.
And we actually know it does do that. We had a student do that.
It has done it. Okay, it has done so.
It'll get better.
Not a zero. We're hoping it gets better and better. Yeah. Okay, so let's go make a scene. well, not that kind of scene. Let's make a physical scene. And usually, so here's one of these functions that we use all the time to initialize ISET. And there isn't a lot that happens in initializing, but a couple of little things. We keep track of what you're doing, the different scenes that you might have worked with and put up in a window through a very minor little memory, a little data, not even a database, just a little structure that remembers what you've been working on locally, and that gets initialized here. And then I've already told you that you can see various scenes by just typing scene tab. And if you want to know something about creating a scene, we have tried to keep our software documented well enough so that you can type doc on the function that you're looking for and get a reasonable description of what the function, how to call the function, the different types of parameters you can use in it, and to go and create any particular kind of scene. We do our best here, and then of course the tutorials and scripts are also available for doing that. One other thing that David and Nicholas got us going on, and that we do a lot of now, is many of these functions, pretty much all, well, a lot of functions, maybe not all, have at the top of them have examples of how to call them. So, and those are stored in the function. While you're writing the function, you kind of maybe have a little test example. And if you wanted to see what were the examples for scene create, this one happens to have a fair number of examples. And so example one, this is how you could create a scene.
But can you just go back to what you did there to get all those out?
Sure.
Went by a little fast.
Sure.
IE examples print. There we go.
That's right. And we try to keep these up to date. And so, for example, here's a particular one. I'll go create, here's one that I could just evaluate it in right there. And so I've now, when this returns, I will have created a scene, and I could look at it inside of the scene window to see what that particular one created. So created a simple scene where these are changing in different intensities equal 10 LL star is a C-Lab convention. Yes, we have a lot of international standards like the CIE standards and so forth built into this. And this makes a set of bars that are each stepping up in intensity by 10 units as we go along. So these are some kinds of things that you can do in creating the scenes. But let's go to an even simpler tutorial. Let me see if I can find my. Okay, there we go.
There we go.
Okay.
And for those of you playing along at home, which I'm doing, you just type edit space T_scene introduction. It'll just bring it up once you've got ISETCam on your path, and
Perfect.
you'll be looking at what Brian's looking at.
Yes.
And I did just verify that it runs, so that was very exciting.
That's always
good. Yeah, always good.
Yes. So we've seen the doc to scene create, and now I'll create. This is a scene that's really, really commonly used in camera evaluation. It's a scene that's based on a color chart like this. This is sometimes called the gray tag chart or the Macbeth color checker, and it's been around for a really long time. And it's got various properties that were selected by people. You remember, Dave? I don't know when people built it, like in the 70s or something.
Cal McGamey built this thing, and it might have been earlier than the 70s, but 70s sounds about right.
And they were using it for color television testing and so forth. And when the scene comes up, you can remember, by the way, that I had this other scene a moment ago, and I didn't lose it. When I added to the scene window, it's still there if I need it, and I could come back here. And the properties of the scene are shown in this little window here. I'll make it a little bit bigger by clicking on it. When we're now going to start talking about units. And, when we made this thing, it's not just pixels. I know a lot of computer science is, well, what have you got? I've got a 256 by 256 or 1024 image, but that's not what we wanted here. We wanted an image that represented real physical quantities, real physical units. And so when we built this one, we specified, well, what's the horizontal field of view? Well, it's 10 degrees, okay. And because of the ratio, we can calculate the diagonal field of view in degrees. How many rows and columns? Well, we're only representing it very coarsely sampled. And it's at some viewing distance, 1.2 meters. And that means each sample, the spacing is really pretty wide, 140. The whole thing is 140 millimeters by 210. And this is the number of samples. So you can see that the sample spacing is actually a little north of 2 millimeters per sample. So we're trying to keep track of all that stuff for you, right? That's the kind of thing that we don't want you to have to calculate and recalculate, and sometimes you'll make an error. We try to get rid of the errors on our own and do that stuff ourselves. The scene is actually represented as a spectral scene. It's showing up here, as of course, it's just an RGB because that's what we can show. But it's actually underlying it, the data that we're showing, that we're representing for you here, there are actually data that are spectral data. And we made these from 400 to 700 nanometers, spaced every 10 nanometers, like that. The mean luminance, or the CIE luminance, that's the Y function in candelas per meter squared. Frequently you'll hear nits. A lot of people are using nits instead of candelas per meter squared. Anyway, they're synonyms. We tell you about the dynamic range, about the illuminant and depth. I'll say something about that in a moment. So let me clear this out. This is here. You can always click on it and make it bigger. And you can do things like plot, how many photons are, let's take a typical, this red one is very striking because it's very red. And you can say, well, okay, that makes sense. That's what we're representing here. This is radiance, and Q for quanta or photons per second, per steradian, per nanometer, per meter squared, coming out of that point. And it appears red because it's got a lot more energy in the long wavelengths than it does in the short wavelengths. And you can also look at other things like, tell me what the luminance is across a horizontal line like this. And it starts out in the white, comes down and down and down. And this is how these guys chose it. Cal McCamey and the people who built the Macbeth color checker designed it to have these properties for useful for color imaging and for color testing.
And you're probably going to show this, Brian, but since this is a real chart that you can buy, it actually has real physical reflectances, and the radiance that Brian was showing was a function of the light that was shining on it. I mean, it gets the units from how much energy is falling and being reflected.
Yeah, good. Let's do that now. I like, that's great. So for example, here's I didn't yet say this, but Joyce is right that I maybe should have, that when we represent these scenes, we represent really three things are all that are connected together, all represented here. One is, most importantly, is the radiance, the light coming that I've shown you that's coming towards the eye or towards the camera, but the light in the scene. And that light that we're describing, the light from a point headed towards the sensor. The other thing is there is, it's just important for imaging, there's an implicit illumination for all of these scenes. And we always represent that fully. So this is the implicit illumination for this scene. And D65 is a really common one that's used in color calibration and targets and so forth. And this is the spectral power distribution from 400 to 700 of a D65 illuminant. Once you know the radiance, and if you believe that it's a uniform illuminance, as I've shown there across the scene, you can calculate what the reflectance is. So let's go look at, well, there's a yellow patch. What's that reflectance? Okay, not much blue. Comes up here in the mid wavelengths and in there. And we could look at the reflectance of, I don't know, a neutral patch. And there it is. Those are literally the data that are represented underneath this image that we're showing. In a lot of cases, you might want to do something like change the, you might want to do something like change the illuminant. So we have D65, and you know what? That's a nice illuminant, but how about if we look at what this might have been if it was illuminated by one of these LED lights. Okay. And so now that's a particular LED light, and it's these lights often look like this. They've got a lobe down here and a lobe over here, and you change the ratios of these two lobes to get the yellowish or bluish or whatever it is that you want. And so now you can see, wow, we change it there. That really changed, that changed for you what's coming out of there. And you can see that there. It's got the little bump down there from the light, and then the bigger bump from the other side. And that's the radiance coming here. But of course, that did not change the reflectance. Reflectance is the same as it ever was. But the light had changed, and therefore the light coming to your eye had changed. And we keep track of all that for you. That's just part of the deal. So I don't like these yellow luminance. So I'm going back to
what's happened to your nice achromatic
what happened?
Your nice achromatic row at the bottom. It's gotten a little yellow there. I will comment a couple things. One is that I use this representation a lot, as Brian we talked about earlier, to represent light coming off displays. And although you could interpret that as illuminated reflectances, I rarely do. And so it is possible to use the scene without ever thinking about the illumination, in the sense that you clocked in a radiance and off it comes, and it's just the step in the calculation. But if what you're doing is thinking about reflectances in the world that actually are illuminated, then this feature of the scenes becomes quite useful and important.
Yeah, that's right. It's not always useful. Sometimes you just want to know what lights come in my way. And sometimes you want to start building a model of the scene with reflectances and luminance, and we'll get even more complex. This one is completely trivial, so I'm not going to make too much of it. But this is a uniform surface, and if you have a screen, it'll be a uniform surface. And we actually have depth maps in here. So these are really the world's most boring depth map. Everything is 1.2 meters away. But by the time we're done, I'll show you some scenes that have more interesting depth maps, and you'll so not everything is useful for every project or every time. There's a lot of stuff here that sometimes you need it, sometimes you don't.
The other thing, maybe this is where you're going, and you've been demonstrating all the things that are in the scene. I think as you said, it's really important to understand that if you want to do quantitative modeling, you can't just have RGB pixels without knowing what their visual angle is and something about their physical overall radiance. But you can also get at all those pieces that you're just showing programmatically, as opposed to through the window.
Yes.
And both methods are very useful if you're exploring. The window is great. You can kind of see what's there and check that it's all making sense and look at it and illustrate things. But if you are writing programs to do an expensive set of calculations, it's extremely important to be able to get at these pieces programmatically, which is something that I think when I use it, I probably do more than when I look at the window.
Same, the same. I think that might be a general. I fully agree with you. That might be a general feature when you use packages. You start out with put the mouse in the little house and click, and then as you learn your way through it, and you learn how to program it, the visual interface becomes less important. But they're both here, and like you, David, I do the same thing when I'm checking my code. Did I get it right? I'll often check it through the window. So here's an example. Now moving on to the gets and sets and so forth. So we have the scene that we had, and this is maybe the one part of this collection of tools. It started so long ago. It was before Matlab had all the tools that it now has for objects, for classes. And but we wanted that feature. So we created many of the entities here, like the scene or the optics. We created them as structs, as MATLAB structs, to keep things together. And the newer code, like an ISET Bio and ISET 3D that I'll mention later, uses classes and objects. But this is the ancient code, and this ancient code uses structs. But we still treat it more or less like it was these were objects. So you could query this thing, say, oh, get me your name, please. Okay, and so that scene get, tell me your name. And there it was. Tell me your horizontal, H for horizontal field of view. Oh, okay, 10. And notice that matches what's up here. It was telling you it was 10. But as David said, you could get it programmatically also. So now then there's many features. You have to kind of look at scene get to see all the different things that you can get. You can get a ton of stuff. You can ask it a lot of questions about itself. And a lot of our knowledge about physics and calculations are built into those get functions.
And everything you can get, you can set, right, Brian?
No, but that's a good point.
Most everything.
Well, you can set there's a kind of a core set of things that you can set.
Like horizontal field, for example,
which we're about to do. That's exactly right. But you can get a zillion things.
Sure.
Yeah. That from all the core things that can be derived. Like
calculated. Right.
So the gets.
And there's a kind of, maybe, you're probably about to say this, but there's a really important reason for that, which is that you don't, if you allowed everything to be settable, it would be pretty easy, but either you'd have to work very hard in the code to have some kind of implicit rewriting of other things to keep it all self-consistent, or there's a good chance that the parameters in your object would become inconsistent. So for example, you could set a physical width and a field of view in degrees and a distance that just didn't go together, and that would be bad. So we only let you set the core set of stuff, and then there are other things you'd want to know about that are derived from it.
Right.
Well, good. So we've got the horizontal field of view. Now we're going to do, this is one of the things you can set, the horizontal field of view. So I've just changed it from 10 to 5. And now if I ask what it was, well, it's 0.5. I set it to 0.5 and I check, and there it is. So now I'm going to take this modified scene where I've changed the field of view, and I'm going to replace the current scene with this one that I modified. And now let's just refresh the window and have a look. And you see it shows up in the window correctly as 0.5. And we try to keep track of all these things for you. Okay, and
I'm laughing because there's what we just talked about right there in the tutorial.
Yeah. Yeah, and that's right. This is the gets and sets and the relationship between them and so forth. And here are just some more examples I'll go through quickly. The distance, you can get it. By the way, there's another, I guess this is here so that I can say that for some of the properties, you can ask for explicit units. Maybe you didn't want it in the default, which is meters, but you wanted it in millimeters. So you could go get it in millimeters, and 1.2 meters is 1200 millimeters. Maybe you wanted to know the scene sample spacing in millimeters, and there it is. It's 0.1 millimeters, 0.109, so 109 microns. If you remember that you've got a scene distance that you're at, suppose you move the thing closer to you from 1.2, you moved it closer to you. Well, that changes the implicit spacing between the points. So now, instead of 0.109, the spacing between the points is also halved because we've moved the whole thing closer to you. Okay, and we could have done the same thing last one here. change, say, you know what, it really wasn't half a degree, it was really a quarter of a degree. And now the spacing changes again, and I can I don't like these dots, so I can actually tell in microns, oh, it's 27 microns, which would show up like this if you were putting it in meters. Okay, so that's just all the properties of all of the objects are kind of like that. The scenes, the optical images, for when I get to them later, it'll be the sensors are like that. The image processing things are like that. And similarly, David and Nicholas have built the retinal simulations, the cones and so forth, with again the same kind of feel to it. You can get things and set things, and we keep it together for you. So the other thing I wanted, I'll show. I just kind of build up a little more complexity. Over the years, a number of us, especially Joyce, has worked to go and create much more complex scenes. So this is one I think you measured in the lab some number of years ago using with some students. And this is a scene that actually the spectra were measured for all the different parts. So again, it was measured like this, and it has an implicit illuminant that looks like that. And you can do the same thing with it. Each one of these is an actual surface and an actual reflectance and so forth. And so these are much more complex scenes. And we have a fair number of them. We have only a few in the GitHub repository because they're pretty large. But we have them, but we have many more of them. Let me see if I can quickly get to it here. In this Stanford digital repository, and there are scenes here that Joyce measured over the years of all kinds of things, of fruits and vegetables, and
yeah, and just to say that these were captured using either a multispectral imaging system that I put together or a hyperspectral imaging system. And we don't have to go into detail. That's explained in the wiki page, but that means that there was a camera involved and a bunch of lights or a bunch of filters, and so we could capture energy in many different wavebands. But it also means that it's still two-dimensional. Brian will talk a little bit about the direction we've been going for 3D, but these are two-dimensional.
Yeah, that's right. That's a very nice point. These are spectral, and here I'm just showing you what they look like this guy's face. Joyce actually collected a lot of faces. We have a whole database of faces, and many objects. This just gives you a sense of what they're like. You can get these anyway. There's ways to get them from inside of Matlab, yeah. So this guy's actually in there, but the many others that are there are not. Yeah,
in our wiki page, we have a wiki page on this. Gives them the link to how they could download them if they want.
Exactly.
So before you go further down in this script, I think up above, it's also worth mentioning, you talked about, you can set and you can get various things. How would you know? An important thing that's up there online, I don't know, 130 and 131 is that if you type doc scene get or doc scene set, it would actually tell you a lot about what you could set and get and how you ask for the units and these kinds of things. So you don't entirely have to just guess or know.
Yeah, no, that's important. That's important, and those we really tried. To get those right, but always double check, and you should never be worried about looking at that code. So these are the various things that you can set inside of the scene, and we're always trying to update it and give more examples. So we've touched on the scene create. I should have added here, if you have, we have these multispectral files. Actually, Let me just do it. We also have ways of letting you, suppose you've got your own favorite RGB file. I don't know, here's the multispectral files. But you know, we each have things that we like in this world. And so here are a bunch of things. I don't know, here's some bears. Bears are good. So you can read an RGB file in. I think you did this in your tutorial.
Yeah, I went through, this is something I use a lot, what you're about to demonstrate, and I did do it in the tutorial we recorded last week, which we'll put up somewhere soon.
And the warning message you get here is that a default display is used.
Yes, yes. Actually, I'm gonna look for the one I really like. Well, anyway, let's go get the zebra this time. Yeah, so I didn't tell it what display, and it's telling me this is the display that I'm going to use. And those of you interested in aliasing and spatial frequency analysis, this is a good one. And you know, it is actually a spectral scene, even though it renders as black and white. So this is, again, and you can take any JPEG, PNG, any image, and bring it in, pretend it was displayed. David has lectured about that, and it'll be up before too long. Okay, you can then do things like plotting. There's all kinds of stuff you can plot. Same thing as we've been saying for all the other methods that if you want to know what kinds of things you can plot and what they look like, do a doc and you'll see that you can plot various things. And then you know, that thing I did about adjusting the scene illuminant and changing it, and here it is. I took that scene that was yellow a few moments ago. Here it was yellow, and I changed the illuminant and I made it more neutral. And so there you go. The reflectances are preserved, but the illumination has been changed. Okay, so I only wanted to do one more thing. So guys, since we're going to roll through this last bit, if there's anything that you really wanted to, this is the moment to gather final thoughts.
Well, let me just say that I think this is, in fact, I know where you're going. That's great. On this scene stuff, you know, obviously, if the scene just existed and you couldn't do anything with it, it wouldn't be all that exciting. And but what we'll talk about in future videos is how, given a scene, you can specify an optical system and compute the image that arrives at the sensor or at the retina from the scene. And the fact that the scene stores all these physical units and is specified that way is what enables that calculation to be nicely encapsulated. And so in addition to scenes just describing the scene, they give a format from which we can compute. And that in some ways is the point of having them.
Yeah, that's important. It can actually do stuff with this. and I'm not doing it right here, but that's next. And David did some in his other in his lecture that we'll put up for this tutorial. And I'll do more stuff in the other path before long, probably the next week or two. So what I'm doing now is I mentioned that there's a whole bunch of other repositories that do other kinds of things. And here's an example of one of the repositories. Let me just clean this. Let me just denoise this. I ran it. This is actually a graphics 3D rendering of a scene that it's very low resolution, 256 by 256, because I wanted it to run very quickly. But it's a graphics rendering of a scene that doesn't exist. It's a scene that we just made up out of whole cloth that we, control. So these are all the chess pieces on the board. There's some illumination, and it is what it is. Rendering it actually because it's a high dynamic range scene. But something I didn't say is that when you look at these windows, sometimes you want to control what it looks like, but the gamma, or use using, if Ted Adelson or his students ever listen in here, we implemented one of Ted's high dynamic range rendering methods and put it in there.
Really useful too.
It's
Right.
been extremely useful over the years. Thank you, Ted. And these two are controllable. I'll change the light in a moment, but I also wanted you to see that in this particular case.
Wait, right before you go
Yes.
there, the gamma thing, just wanted to point out that you're doing that just so you can look at it visually, but it's not changing the underlying representation. That's just how we're rendering it.
That's true, and that's important. Yeah. And this is the depth map. So the closer things are brighter, the darker things are a little further away. And so in this case, we actually have the depth map for a lot of computer vision applications, estimating the depth or knowing the depth. When you're rendering with real optics, you need to have information about the depth, and so that's part of this. And that package is I'll end with by showing you the relationship to them. That's called ISET 3D for building interesting scenes. I ran this sort of in the background while these guys were talking, just to speed it up. But basically, the calculation is we have a whole bunch, about 60 or so different scenes of really quite complex, from daytime driving scenes to indoor rooms to chess sets to all kinds of. There's a whole bunch of scenes that are now up on the Stanford Digital Repository, and they're all available, to be used in this framework. So what I did here was just read one of them. So I said, go get me the chess set scene. And that gave me a recipe for how to render it. I did the usual thing of setting some parameters. And then I wrote it out, I rendered it, and then I showed it in a window. And that was what came up for you. I'm going to do that again. I'm going to delete all the lights. And I'm going to change the lighting now on the chess set. And so the light that I have now in the chess set is, you can see it's got the word rainbow in it. And I'm now saying, okay, there's my recipe. And this is the one with the rainbow. And it takes us, I'm at home on, it's kind of a slow computer, and it's writing some stuff out. And then in a moment, it's going to upload this to a computer where I have a GPU, an NVIDIA GPU that runs CUDA. And it will render it with the new lighting instead of this lighting. And I don't know why this is so slow, but anyway, there it is. It's starting to upload. The rendering itself, it only took it 3 seconds to render. All the slow stuff had to do with my computer and the internet connection and stuff like that. And so now we've re-rendered it here with a different light. And you can see it's noisy because I wanted it to go faster. I do have a graphics denoising stuck in here just because sometimes I want to run it quickly and then denoise it. And so that'll clean this stuff up. And now we've got a different light, and it can be quite complex lights. These are called sky maps. They're really defining the lighting all the way around the world. And we can put in point lights and spotlights and all kinds of lights. For those of you interested, I find the question of how lighting impacts, ever since I've known David, we've been talking about lights and their impact on perception for probably 35 years on now. And there's wonderful, the new developments from Roland Fleming and from all kinds of people around the world about thinking about appearance and lighting. You kind of need tools to create stimuli where you control them. And I first watched David do this in Santa Barbara a number of years ago, and still with us, but easier now. A few lines of code and off you go. And so that's in a way, that's, I would say, our goal for this is to make it easier for the next generation of student to do things that we thought were hard, but hopefully will not be hard for you. And we're assembling these tools with that goal in mind.
And also, I was encouraging Brian to go through this so they could see kind of where it was going, that there are scenes that can be more complex and that you can represent depth and very complex lighting and things like that, even fluorescence. But we're not talking about that. I mean, it's more of just to show you where it can go, and also that we've done a lot of work for people that they can take advantage of, so we don't have to tell them how multispectral and hyperspectral imaging worked and what we did. We already did that. Those data are available. They don't have to know how to use PBRT and all these other things, ray tracing, and what you did to create these very complex scenes. Luckily, you're creating them and you're making it available for people. So,
but some of them definitely need to know so that when we stop doing this, they can keep it up.
Yes. Hopefully there'll be a user community who will continue to make to push the envelope about representing scenes, right?
Exactly.
And I think that I was going to say, I think it's important just to maybe again step back a little bit here. When we think about the original ISETCam scene, we might say that there was kind of surfaces and luminance, everything was flat, except maybe you could put the depth map in, which I never did. And but the reason for that was because we think about the purpose of perception to being representing stuff that's out there in the world. So even for simple things, we wanted to think of it as at least perhaps being factorizable into world stuff. And computer graphics has just enabled us to really up the game in terms of pushing the description of the stimulus or of the scene out to the 3D world and still accurately compute what's going to arrive at the image plane or the retina or the sensor, which is the proximal stimulus, as we would say in the perception biz, for reasoning back to what was out there and developing perceptual representations. So the ability to sort of do this in an efficient, controlled way with units is really an important building block for building theories of how the brain creates perceptual representations that bear some correspondence to what's out there in the world.
Yeah, I mean, we're amazed at what our colleagues in computer graphics have put together and enabled us to do. These are all rendered scenes from PBRT that are all part of the distribution.
Right, and these were generated using ray tracing, physics-based, and for our colleagues who are working in generative AI, it's still very useful to be able to go back to the real physics of a scene, even though they're going to try to approximate it using their AI methods.
Yeah, and they've got all kinds of nice features. You can see the depth of field in some of these scenes, and anyway, it's just they did a really nice job, and we're just trying to build on their work. So let me just end. I don't mean to push too fast, but we've got this big collection. ISETCam is kind of at the bottom where we use it. We use it in various ways to build complex scenes with optics and sensors and so forth. And then ISET Bio and is a really, if you're going to take these scenes, and we'll do optics next and go into the retina, ISET Bio is for you. And there's a bunch of many routines in ISET Bio, and David is on the path for doing that. But we've already actually published some papers. Anyway, ISET Fundamentals, ISET Bio Principles, David's CSF generator is important. There's another one that I meant to copy here. And then for those of you interested more in engineering and engineering applications and driving and optics and so forth, high-density sensors, there's a collection through this ISET 3D. You really kind of need to get into these complex scenes for that direction. And you saw those scenes. And again, if you get into this ecosystem, we've been building tools for the software itself. So David's example test toolbox for checking things. We try to validate our code to make sure we make changes. We haven't stepped on our calculations, that everything numerically is still correct for unit testing. And we're just getting started now we decided to pull out the tutorials and make a separate thing just where we can enrich the tutorial experience. So that's, okay, if you've made it to this part, even if double speed, thanks for listening.
Great, thank you.
Okay, thanks. Stop sharing. I
And
probably,
recording? You gonna keep recording?
no, well, I could, but I was gonna try to stop. What do you think? Pause, there it is. So I'm just gonna stop the recording. There we go.